from this side we have a smaller electronegativity, and for this right hand side, a larger electronegativity. Yeah, means that the larger value means that we tend to acquire electrons. That's why it become a negative ions. Okay, and then besides that, I think this is also we have to know this. Okay, it's atomic bonding. Okay, in solids. Okay, basically I think there are two types: primary interaction bonding and secondary interatomic bonding. Okay, there is the two main force of attraction that holds atoms together. Okay, and we call it as a chemical bonds. Yeah. Okay, this is all the chemical bonding. Okay, and basically atomic bonding is solid. If I don't know, if someone asks you, okay, it's easy. Can be divided into the primary interatomic bonding, and secondly is a secondary interatomic bonding. And then for the subset of primary interatomic bonding, they can be divided into three domains. Okay, first one is the ionic bonding, second one is the metallic bonding, and third one is the covalent bonding. Okay, for the secondary interatomic bonding, we have only one dual forces here, or bonding. Okay, chemical reaction between element involve either receive or releasing or sharing of electron. Okay, so we will learn about this. I think this is just recap. Sharing of electron means that we have a covalent bonding, and releasing or receiving electrons means that we have either ionic bonding. Yeah. Okay, and then we move on. Okay, so for the ionic bonding, as I mentioned, it is a meaning receiving or sharing, or not receiving or releasing electrons. Okay, often found in a compound composed of electropositive metals. Okay, like magnesium. Okay, aluminium, sodium. Okay, that is all the electropositive element, and also they combine with the electronegative elements. We call it as a non-metal. Okay, basically, we have learned this, I think, during your foundation. In order for us to have this ionic bonding, we must have a complete, I mean, the complete of electron. Yeah, so means that let's say for magnesium. Okay, in this example is sodium. Okay, sodium, we have extra one electron here, and that is going to be donated to the chlorine, so that the chlorine will accept this electron, and have a stable octet of configuration. Yeah? So we are not going to have this electronic configuration, because we have learned this during your foundation. Yeah? But what I'm stressing is that for the atomic bonding in solids, it can be divided into two. There is a primary and the secondary. Okay, the primary interatomic bonding can be divided into three. There is the ionic bonding, covalent bonding, and the metallic bonding. Yeah? So this slide is dealing with the ionic bonding. Okay, and for this one, electron are transferred to form a bond. Okay, you can see from here, means that the one electron outside of the sodium uh, being transferred into the chlorine. So don't worry, it's not about the chemistry. Yeah, this course is not about the chemistry. Okay, so basically for the ionic bonding, we need metal and non-metal. Metal, the one who donates the electron, and non-metal is the one that accept electron. Okay, and then we move on. Okay, and this one just want to show you, you have, for magnesium, we have two extra electron. For sodium, we have one extra electron, and then donated to the oxygen. We need that needs, two electron to become to have a complete electron configuration. Okay, then we move on. Okay, and then example of ionic bonding. Okay, let's say sodium chloride, magnesium oxide. These all are example of ionic bonding. As I mentioned, there are electropositive element, that is metal, and then electronegative element, that is the non-metals. Okay, this one, all this side is the one that give up electron or donate electron, and this one, this side is the one that receive the electron. Okay, but the properties this is the most important about the material science, yeah, or engineering. Okay, means that the ionic bonding, the properties is that they are normally are solid at room temperature, yeah, and then they have high melting and boiling points, and hard and brittle. Okay, why? Because we know that metal is ductile, but when they have a ionic bonding, means that they become hard but brittle. Brittle means that easily break, like glass. Okay, but they are very hard. Okay, and then they are poor conductor of electricity in the solid state. Okay, we know that, but in the molten state, they are a good conductor. Okay, so in the solid state, let's say sodium chloride is not a very very poor conductor, but let's say if you melt it or in the molten state, they are a very good conductor. Okay. Okay, and this is the covalent bonding. Covalent bonding is about the sharing of electron and negativity. Yeah? I mean sharing the electron. Okay, let's say this one we should have a similar electronegativity because we want to share electrons. Okay, a bond determined by the valence s and p orbitals. Yeah? You have learned this, yeah. In your foundation, you have s orbital, p orbital, and d orbital as well. Okay, but we are not going into detail. We just want to know the properties of the covalent bonding. The properties of the covalent bonding are they are very poor electrical conductor in all phases. Okay, either in a solid phase or in the molten state. Okay, but they have sometimes they are very strong and hard. Okay, often found in the non-metallic element. Okay, molecules such as hydrogen, chlorine gas, hydrogen gas, and fluorine gas. Okay, molecules containing dissimilar atoms. Okay, like this one, CH4, methane. Okay, this is classical example. When they are shared, the electron means that they have the complete electronic configuration. That's why they can form the covalent bond. Okay, hydrogen has one valence electrons, means that it needs one more to have a stable electronic configuration, and then that's why they share with the uh, carbon atom, yeah, because the carbon atom have four extra electron. Okay, means that they needs not extra electron, but they have four valence electron that needs four more electron, and they shared with the four hydrogen. Okay, another solid compound composed of elements that are located on the right side of the periodic table, like gallium arsenate, indium antimonate. All these are uh, form the covalent bonding. Another example is the silicon carbide. Okay, you can see this in your periodic table. Yeah? So let's say if I ask you what type of bonding in silicon carbide, is definitely it is a covalent bonding. Okay, don't worry, there is an example of it later on. Okay, so that we are more understanding. Okay, this is as I mentioned, example of covalent bonding. Normally occur in the hydrogen gas, chlorine gas, and fluorine gas. Okay, somehow molecule containing dissimilar atom like methane just now, water, nitric acid, or hydrofluoric acid. All these form covalent bonding as well. Another important thing is that, let's say, diamond. Okay, in a carbon can exist as diamond, can exist as graphite. Definitely, they have a covalent bonding. Okay, and also as I mentioned, the famous example is the silicon carbide. Okay, then the third type of the primary interatomic bonding is that the metallic bonding. Okay, metallic bonding, it occur when some electrons in the valence shell separate from their atoms and exist in a cloud. Okay, you can see the cloud of electrons here. Yeah, so the valence electron are form of sea of electron. Okay, means that we have the positive charge metallic ion, this one, because the negative, and we have the negative electron cloud. Okay, normally it's found in group 1A and 2 elements. Okay, this is for metal. Okay, we call it as a metal and its alloy. Okay, and it arises of the sea of donated electrons, 1, 2, or 3 from each atom. Okay, that's why we have the sea of electrons. Okay, and then there are, what are the properties? I think their properties are um, contrast with the ionic bonding. Yeah, I mean they are very good electrical conductivity because they have the sea of electrons exist in their system, and also they are very ductile, as I mentioned to you. Ionic bonding is brittle, but metallic bonding is ductile because metal is a ductile. We can use this property later on, I think, in the chapter 6 to show the benefit of this characteristic of the metal. Yeah? And also they are very opaque. Opaque, they didn't allow light to pass through, but we can use this, as I think in our first lecture. All the metal has their own DNA. That is the microstructure. So by using these properties, we can actually identify what sort of metals that are present in the system. Okay, and then I move on. Okay, this is secondary bonding. As I mentioned, the most important one is the van der Waals forces. Okay, uh, for this, the only important thing is that about the mechanism. There are three bonding mechanism. Okay, we have van der Waals forces, but actually there is a three mechanism. There are same forces. There is the van der Waals forces, the weak forces, but we have three bonding mechanism. Okay, the first one is the fluctuating induced dipole bonds. Okay, we have the similar elements. Okay, and then they are attract to each other. So basically, for the fluctuating induced dipole bonds, it is exists in the let's say within the inner gases and the symmetric molecules. Okay, example like the hydrogen gas, and this is the of the fluorine gas. Yeah, chlorine gas. Also, this is the mechanism, bonding mechanism that exists in the hydrogen and chlorine gas, that is the fluctuating induced dipole bonds. The another type of the mechanism, we call it as a polar molecule induced dipole bonds. Okay, we have different elements. Different element. There is hydrogen and chlorine. Okay, you can see this, or hydrogen and fluorines, mean that from the previous one we have the symmetric molecules, and for this one we have the asymmetric molecules. Okay, and then lastly we have the permanent dipole bonds. Okay, this one is the secondary bonding, hydrogen bonding. That is, if we have, let's say, PVC, this is a polymer, yeah, polyvinyl chlorine. So let's say we among there is a repeating units, but among them there exists a van der Waals bonds. Yeah. Okay, I think we have learned. I think it's if you have any problem, just let me know. Okay, this is example, so it become clearer. Okay, we just go for it. Okay, let's say what type of atomic bonding for the following of materials: methane. Okay, I'm not going to ask you, but I think you can guess. Methane we have, let's say, covalent bonding. Yeah, okay, methane we have covalent bonding. And how about the magnesium oxide? Okay, I think I let's say in the chat box, if you want to answer. Okay, uh, okay, one of you, if you want to try. Okay, if you want to try magnesium oxide. Okay, there is I think answer from one of you. Okay, ionic bonding. Oh yeah, no, very fast. Okay, Mama Afzal, thank you. Daniel, thank you. Okay, I think it's quite straight. Okay, this class is very very good. I think it's this class is like a kacang putih. In Malay we call kacang putih, or English peanut. Okay, and then that's great. Okay, great, good class. Okay, and then tungsten. Okay, of course we have metallic bonding, graphite. We have learned covalent bonding, and the sodium chloride, again it is the ionic bonding. So all the work example that we have done in the class, definitely I will upload either in the WhatsApp group or in our MS team. Yeah, okay, because we have done. So let's say if you have different opinion about this bonding, just let me know. Yeah, okay. There is so unique white peanut. Okay, white peanut. Okay, great, great, yeah, great. Okay, Okay, great. Okay, so I want to see the participant. 61. That's great. That's good. That's good. Okay. Okay. Then we move. I think this one is, I think, just recover from your just recap from your SPMM foundation. Okay, this one, I think this is the one that we have learned before. Yeah. So the major class of material, of course, you know, metal, polymer, ceramics, and by combining this, we can produce composites. Okay, and we know that the structure of material determine their properties. Okay, we know that properties can be changed during processing due to the change in structure. Okay, there is a continuation from our previous lecture with today's lecture. Yeah? And today we are going to learn the structure of material. Okay, and then that's why we need to understand the structure of the materials. Okay, and then finally today we also be able to differentiate between primary and secondary bonding, and then predict the type of bonding based on the electronegativity. Okay, what else? Ada ke message? Tak ada ya. Okay, great. Kejap guys, sorry about this. Okay, current session is an important for us. Okay, sorry guys. Okay, we move on. Don't worry, I think this is quite straightforward. Okay, okay, the straight for today's, I think the most important one, but I think it's going to be a straight one. Instead, there is no crazy formula or about it. It's just a straight one. Okay, we want to, let's say, for this learning outcome for this topic for today's lecture is about the arrangement for crystalline and non-crystalline materials. Yeah. Okay, sometimes I ask you to sketch. Okay, this is where you know you need to sketch. Okay, let's say for the arrangement for crystalline and non-crystalline, don't worry, I think we will cover it. Okay, and then draw the unit cells, whether it's phase centicubic, body centicubic, and we are not going to have the hexagonal closed pack. Yeah, rather we have the simple cubic SC. Okay, don't worry. I think later on, as later on I will show you. We are not going to cover the hexagonal closed pack. We only cover phase centicubic, body centicubic, and simple cubic. Okay, sorry about that. Okay, and then we want to find the relation between what is the unit cell each length and the atomic radius for the FCC and BCC and SC as well. Simple cubic is very straightforward. Okay, I think it's just straightforward punya relation. Okay, I will define what is the unit cell each length. Yeah. Okay, and then finally, okay, we need to calculate the density. Of course, it's using the formula. Okay, I think it's also quite a straightforward punya formula. Okay, need not to memorize. Let's say a face-to-face exam. Although we are not going to have this during, let's say, face-to-face exam also, we will provide all the formula. But what we are stressed is that your understanding and your analysis on the problem that we give to you. Okay, that is the most important part. Okay, so sometimes I might ask you, to sketch. Okay, basically this slide. Okay, as long as you can sketch, I think this one is okay. Okay, solid materials. Okay, either it's a polymer, either it's a whatsoever metals. Okay, especially metals, we call it as solid materials. And then the solid metals can be divided into two: crystalline material, okay, and non-crystalline material. Okay, the non-crystalline material we also call it as amorphous. But let's say if I ask you the solid, how many types of solid material, you just name it is a crystalline material and non-crystalline material. Okay, easy. But let's say if you can put as amorphous, that's a better one. Okay, for the crystalline material, what we define as a crystalline material? Okay, the atom that's packed in the periodic three-dimensional arrays. Okay, means there is a repeating unit. There is a very nice arrangement. Okay, very systematic one, and we also find it in the metals, some polymer, and also many ceramics have this crystalline materials. Okay, for the crystalline material can be divided into polycrystal and single crystal. Okay, for the semiconductor, of course, we need for semiconductor materials we need the single crystal. Single crystal is very expensive and it's very hard to produce. But it's to produce means that we need a expensive processing equipment to produce it. That's why it's very expensive. So for the polycrystalline, how we differentiate between the single crystal? Easy. Okay, can you see just me how draw? Okay, if you let's say you draw like this, and there is a boundary there. Okay, this boundary. Okay, all these are the boundary. We just draw, and we call it is a grain boundary. Okay, this is we call as a boundary, and we call it a grain. Okay, and this segment we call as a grain, but the line that separate another grain we call is a grain boundary. Okay, if you draw like this, I think it's good enough. Okay, polycrystal means that we have many grain boundary. Okay, in segment, and completely ordered means that they are very completely ordered arrangement. Okay, just nice. If you draw like this also, it's a good one. Okay, for single crystals, as you see, there is only one grain. Okay, means that it's a material in which the crystal lattice of the entire sample is continuous and unbroken to the edge of the sample. Unlike this one, if you see there are many grain boundary, but this one there are only one grain. I think in your third year engineering material, you will find what is the importance of having this single crystal. Although it's a very expensive process, but sometimes depending on the application, we need this type of the properties. Okay, for the non-crystal material amorphous, okay, the atoms have no periodic packaging, unlike this one. Yeah, this one is periodic. This is no periodic packing. Okay, occurs in the complete structure and in the rapid cooling process. Okay, example of this, let's say if you draw silicon dioxide, our sand, okay, our glass is made of silicon dioxide. Okay, amorphous means that non-crystalline. So as long as you can draw like this, okay, I think it's good enough. Okay, so what the most important point that we can derive from this slide is just that solid materials can be divided into two: crystalline material, non-crystalline material. And the crystalline material can be divided into two. There is a polycrystal and single crystal. Okay, what is meant by a polycrystal is a complete order in segment. This is how you differentiate between polycrystal and single crystal by having the grain boundary. Okay, this is just only one grain. Okay, for this one there are many grain. Okay, then okay, another term that is a very important one. Okay, this one I think you can refer to all the textbook. Okay, even this one also is from the textbook. Okay, what is the most important one is that later on we will learn about the unit cell, and we also have the, let's say, the lattice. Lattice is the line network in a 3D. Okay, that's why we call a lattice. Okay, most metal exhibit a crystal structure which show a unique arrangement of atoms in a crystal. Okay, later on we will see it. And then lattice plus the unit cell. Unit cell means that in the crystal structure, this unit cell is the subdivision of the lattice that still retains the overall characteristic of the entire lattice. Okay, this is what meant by the unit cell. Okay, this is the repeating unit. Okay, all the crystal structure is made of the unit cells and lattice. Okay, lattice plus unit cell become the crystal structure. What is lattice? Lattice is just the lines network in a 3D. Okay, what is a unit cell? The atom that's arranged in a repeated manner. Okay, so quite straightforward. Lattice plus unit cell become the crystal structure. So the definition.
I have a question, sir.
Oh, sorry. From Yan, right?
Yes. For one unit cell, is it always one atom, or can it be multiple atoms?
Okay, good question. It can be more than one atom, and then we will learn. Definitely, you are ahead of us. Is it okay? Can I answer that in our next slide? Is it okay, Yan?
Yep, sure.
Then great, yeah. I think you follow. I think that's great, great question. Yeah, means that later on we can see, crystal structure actually, they have the arrangement of atoms. Okay, typically of this, if you talk about elements, we only have one element, but the arrangement of atom is quite different. I think later on we will see this. If I'm not answering your punya question, yeah, just let me know, yeah, when we reach that slide. Okay, and then we move on. Okay, and then this one, let's say every atom, every, let's say sodium chloride ionic bonding also have their repeating unit. Okay, as I mentioned earlier, this is just more information from our previous slide. Okay, we have defined what is lattice, and we also have defined what is the unit cell. Okay, and then a lattice plus unit cell is become a crystal structure. Yeah? Okay, and then the most important thing is that, you know uh, what is the crystal, what is the unit cell, is that it is just the repeating unit of all in the crystal structure, and how it arranged is depend on the lattice punya arrangement. Okay, and then we move on. That's good. Okay, this is our crystal system. We have many we have 7 crystal system, the most important one. Okay, we have cubic, hexagonal, tetragonal, rhombohedral, orthorhombic, monoclinic, and triclinic. But in your course, just concentrate on this cubic system. Okay, we only concentrate on the cubic system. Okay, this is if someone asks you, okay, how many, let's say we have the crystal system, we have 7. Okay, we have, let's say, Brevis lattice. Okay, what is meant by Brevis lattice is describe the geometric arrangement of the lattice point and the translational symmetry of the crystal. We have face center, we have body center. Later on, you will find it, what is meant by face center and body center. Yeah? But our system that we concentrate is in the cubic system. That is actually most metals will exhibit of this one. Yeah? Either it's a body center cubic, face center cubic, and hexagonal close back. Yeah? Okay, by adding this 7 lattice point to 7 basic crystal system, we have 14 uh, system. Yeah, means that we have formed 14 Brevis lattice. But don't worry about it. We will only focus on body center cubic, face center cubic, and hexagonal close back, because uh, uh, this I think as a mechanical engineer, you need just to know about this 3 system, mostly that importance. Yeah. Okay, the rest, all the other system is you leave it with material engineer punya task. Okay, and then, okay, this is the most important part that you need to know. Let's say, okay, this is the crystal structure of metals. Okay, most metal, when we melt it, okay, become liquid state, and when they solidify, they are going to have three common structure. Yeah? Okay, these 3 common structure. Okay, namely is a body center cubic. We call it as a BCC. Okay, body center cubic, and then we have a face center cubic. Okay, like this, and then we have the HCP. As I mentioned, we are not going to touch this. Okay, we are not going to touch this. It's just your knowledge, most of them. But and then we have the simple cubic. Let's say if I ask you, or someone asks you to draw it, okay, what is meant by the body center cubic? If you can draw like this, is marvelous. But the one that in the below one, I think is more realistic for you to. But you can, if you can draw this, I think it's good enough. But let's say if you have this cubic system, you draw a cubic, and then you put let's say atom at each corner, 1 2 3 4 5 6 7 8, and then you put the one in the middle. this one. So this we call as a body center cubic. For the face center cubic means that the every phases of this cubic there is a atom 1, 2, 3, 4, 5, 6. Okay, and then at each corner you just put another 8 atom. So this one, as long as you can draw like this, I think is good enough. Okay, in the my example as well, it's just a matter of redraw this. Okay, for simple cubic, I think it's much straightforward. If you can draw like this, I think thumbs up. But the below one is also is good answer as well. Means that simple cubic you have 8 atoms at each corner. Okay, for face center cubic you have 8 atoms at each corner, and then there is also atoms at the every phases of the cubic. Okay, one, okay, in front, this one, 3, 4, up and below. For the body center cubic you just draw this. Okay, only one in the middle and the rest is at the corner. Okay, if you have any problem just let me know. Okay, so how we define the atoms? Okay, this is the most important part, and then later on when we calculate the density, or when we calculate the density, we use this concept. Okay, so as I mentioned, for the body center cubic, okay, how many atoms are there in the system? Okay, first one, we only have one atom in the center. Okay, this big one. Okay, this one is not shared. Okay, and the number of atoms at each corner. Okay, we have 1, 2, 3, 4, 5, 6, 7, 8, and then but this one is actually shared by another 8 atom. So we have 8 times 1 over 8. That is, we have 1 atom. So the total number of the atoms that present in the body center cubic is 2 atoms. Okay, how we calculate it? I think it's quite straightforward. I mentioned to you. Okay, at each corner, corner is shared by another 8 atoms. So that's why 8 times 1 over 8 becomes 1. Okay, the most common metal that exists in the body center cubic after solidified from liquid state, okay, is chromium, tungsten, molybdenum, and vanadium. Okay, for the face center cubic, how we calculate number of atoms? Okay, quite similar process. At each corner, okay, we have 8, but it's shared by another 8 atom. We have 1, and then we have 6 atom at the each phases. Okay, means that we have 6 phase in the cubic. So at this point, we have to times by half. Okay, because it's shared by only another atom. So 6 times half is 3 atoms. So the total numbers of atoms in one unit cell, okay, is 4 atoms. Okay, for body center cubic, if I ask you what is the number of atom in one unit cell, okay, as I mentioned earlier in my previous slide, unit cell is the repeating unit. Okay, repeating unit of the system. Yeah, okay, repeating unit of the system means that let's say I ask you for the body center cubic, how many atoms that exist in the unit cells of the body center cubic? The answer is 2. How you got 2? As I mentioned earlier, we have, let's say, 8 atoms at the corner, and then we have one sole atom in the middle. Okay, that's why we have 2. Okay, this is how we calculate it. Okay, for the face center cubic, we have 4 atoms, and normally the metals that exist as a face center cubic is aluminium, nickel, copper, and platinum. Okay, and then we move on. Let's say if you have any problem or any question, just be like Yan, because I cannot see, let's say, the chat box at the moment. Okay, just watch it out. Okay, later on I will see in the chat box if you don't want to ask during the lecture, you want to save it at the end, so I will see in the chat box or in the WhatsApps. Okay, in the WhatsApp you can always at instant because I can check my WhatsApps. Okay, and then as we go on, okay, this one we are not going to learn about the hexagonal prospect, but this is how they got the name. And the most important is, I think, quite simple one is a simple cubic. How you draw the simple cubic? You just have a cubic punya draw, and then you just put atoms at the corner. Okay, and for the simple cubic we have only one atoms. Okay, means that the atoms is the resemblance of atoms of, let's say, a manganese atom or what's manganese atom, because this is exists in the metals. It's not like the ionic bonding, okay, like sodium chloride, uh, or let's say alumina or silicon dioxide. They have different arrangement, but your case, you will solely in this topics, you will study or focus on the metal. Okay, this is for the manganese. Okay, then I move on. Okay, this one is just for your knowledge. Yeah, that's why I didn't go into detail. Okay, then I move on. Okay, normally I think this is trend. They always ask you, the relation, okay, between the R. What is meant by R? R is just the radius of the atom. And what is the A? Okay, A is just the H length. Okay, okay, this is A because all the A are equivalent because they are cubic. Yeah, so A is this one. Okay, radius is just the radius of atom. Okay, this one. What is the radius of atom? Okay, R is just the radius of atom. A is the H length of your cubic cell. Okay, so for the body center cubic, what is always, they will ask you the relation between the radius of atom and the A. Sometimes also they call A as the lattice parameter. So the lattice parameter actually is your H length for the cubic cell. So sometimes they call it a lattice parameter, just want to confuse you, but actually they are the same, the same meaning. A is the lattice parameter, or A also as the unit cell H length. Okay, this is your H length. Okay, now we have how we define it. Okay, okay, so I think this one you still remember this is just the relation. Okay, you know that let's say for the DF, how you first what is the length of the DF. Okay, don't worry, this is your DF. Okay, let's say if you have any problem, just let me know. Yeah, okay, DF, and then how we there is a relation. I think this is just the theorem that we have learned before. Yeah? So df squared is actually is just the uh, df squared plus dg squared. Okay, I think it's just the triangle. Yeah? So for the body center cubic, why we need this df? Why we cannot use this? Because we don't know this value or the punya value of or the punya length. So that's why we have to put the diagonal punya relationship. Okay, because for this one actually all the atoms are touch each other. Okay, this one for the diagonal side means that all the atoms are interconnected. There is no gap. That's why in order for us to find this relation, it is advisable, or I think it's a common practice to have the diagonal punya length. Okay, we know that from we have learned before in our simple mathematics, df squared is equal to gf squared plus the dg squared. Okay, now we have, okay, this is simple. Dg is just dc squared plus cg squared. Okay, I think it's quite straightforward. This one, because why we need, and then we need all the relation of the A and R. Again, I stress R is the radius of the atom, and A is the unit each length or lattice parameter. They are have the same meaning. Okay, either let's say if I ask you what is the relation between lattice parameter and radius, means that the relation between the each length. Okay, A is same for all this because we are dealing with the cubic system. Okay, and then we know that df is for r. Why is for r? Because you know this is the radius of one atom that shared at the corner. Okay, and we have 2r in the middle. Okay, this big one, 2r, and then we have another at the corner is r. So that's why we have 4r, means that the radius of atoms. Okay, once we can find this, we know that df squared is just the dc squared plus dcg squared plus gf squared. So by substituting this, it is quite simple for all of you. Okay, and then a squared plus a squared. Okay, and then gf squared, we have 4r squared equal to 3a squared, 3a unit length. So finally we rearrange it as this one. Okay, and then finally we have the relation between r and a of the body center cubic. So we just simplify it, we just rearrange it. Okay, and then we have the this one. Okay, then we move on. Okay, we move on to, okay, this is the relation. Let's say if I ask you to derive this, I think I hope that you should be able to derive it uh, uh, using this method. So basically what I'm stressing is that you need to find the diagonal length. Why we need to find this diagonal length? Because the atoms are touching each other. Okay, different for phase center cubic. Later on we will dealing with phase center cubic. I hope that don't worry. I think there is exercise relating to this. You know, just to make sure that you are comfortable with it. Okay, just the repeating. For me, let's say if you can try later on during the exercise, you can do. I think is you will have more understanding. Yeah? When you listen, is just you know that something, but when you do it by yourself, means that you are more understand. Okay, and then okay, this is the relation between the r is the radius of the atom, and the a is just the uh, okay, sorry for the poor image. Okay, for the phase center cubic. Okay, for the phase center cubic, okay, you can see there is a continuous the radius of atom. I mean the atom are touching each other at the face diagonal. Before this is a body diagonal, but this one I think is quite straight because we know this. So once we have this close, touching of the atoms, means that we can calculate the relation between R and the A of the system. Okay, so again, this is for the phase center cubic. Okay, so means that for we see this one A B C D. Okay, and we know there is a continuous at the phase diagonal. Okay, we can see at the phase diagonal. Okay, and then we know the A. Okay, that's good enough. Okay, and then when this one touch again, before this is body diagonal, this one is phase diagonal. Okay, it's quite straight. I think we got 4r here. So just db squared. Okay, db squared is just we're looking at this triangle. Just dc squared plus b cb squared or bc squared. Okay, then we have this relation. Okay, 4r squared again, and then dc is a because this is the length of the unit cell. Okay, and then also in order for us to find this one, we have this relation DC squared plus BC squared. So for R squared, A squared plus B squared. Then we simplify it. Okay, we rearrange it. This is the relation between the radius of atom and the A, the lattice parameter of the or the unit cell H length. Okay, this is for the facility cubic. Okay, and this is just the summary. Okay, for body centicubic, we have proved that in this atom we have two atoms per unit cell. Okay, and the relation between A and the radius is given by this relation. For the face center cubic, okay, we know that we have calculated before how many atoms per unit cells. Okay, we have 4 atoms. Okay, we have proved it just now. Okay, and then this is the relation. And for simple cubic, I think it's quite straightforward. I'm not showing you the example. A is equal to 2R. Okay, means that R is half of A. Okay, this is A. Here to here is A. And we have R and another R. Okay, because they are touching each other. Simple one. So I hope that by now we have learned uh, the relation between the lattice parameter or lattice constant, sometimes they call, or the unit cell H length with the radius of the atom. Okay, and now atomic packing factor. Okay, what is the atomic packing factor? We call it sometimes is the APF. Is defined as the efficiency of the atomic arrangement in the unit cell. Okay, how we want the most dense one. Okay, later on we will find which of these three systems, body centicubic, face centicubic, or simple cubic, which one have the most packed atom. Okay, later on, and then we will prove by this calculation. So how is the mathematical relation between this APF? Yeah? What is defined by APF in terms of mathematics? APF is given by number of atoms per unit cell. Okay, we have learned this, how we calculate number of atoms in the unit cell from the previous slide. Okay, we know that for, let's say, for simple cubic, it is 1. Everybody agree because we only have uh, atoms at the corner and it's shared by another 8 atom. So 8 times 1 over 8 is 1. Okay, that's why number of atom for the simple cubic is 1. So the formula is number of atom per unit cells. Okay, we call it as a N. And then times by volume of atoms in the unit cell. Volume of atoms in unit cell is just because they are sphere. Okay, this is the volume formula for the sphere atom. 4/3 pi r cubic. Then, as I mentioned, we need to know the relation so that the R will be replaced by the relation of the unit cell each length, so that we can omit the R punya term. Yeah? So that's why we need this relation. Okay, so this is a volume of atoms. Actually, this one is R, 4/3 pi r cubic, but R is replaced by this one. Why we need to replace R with the unit cell H length? Because in order for us to find the APF, we need to divide by the volume of the unit cell. The volume of unit cell is just A times A times A. Okay, this is the volume of the cubic, A cubic. Okay, this is the volume of itself. So in order for us to find this one, okay, we need to replace the relation of the R. That's why we are always find the relation between the radius and the A. So because it's very useful in calculating the APF, atomic packing factor. Okay, the APF for simple cubic, using this relation of formula, okay, you will find this one is 0.52. Okay, later on we can do the exercise whether it's correct or not. Okay, and then I move on. Okay, okay, for example one. Okay, I think we do it together before we have a break. Okay, for the body center cubic, okay, face center cubic. Okay, this is, let's say if I ask you to draw, you need not to draw like this. Yeah, you just need to have a simple cubic, the one that I mentioned in our previous set. But if you can draw this, I'm not opposed to it. I think it's great. Okay, and then for this one, what is the question? Sorry about that. Okay, calculate the APF for the body center cubic and face center cubic. Okay, we use the same formula that before. Okay, same formula, no worries. Okay, this one, this is for example, don't worry, later on I just want you to check whether it's correct or not. Okay, this one we do it together. Okay, but although the exercise, I think your quiz or assignment, sometimes your quiz is a very short one, but you need to produce it because of the one that we have learned in the class. Okay, for body center cubic, we know that, okay, uh, we have calculated the number of atoms per unit cell. Okay, we know that, we have proved that for the body center cubic we have two. I think everybody agree. For face center cubic we have four. Okay, and then we have proved it like before. But let's say if you have an query, just let me know. Okay, and then times volume of atoms in the unit cells. Okay, it's the same formula for our 3 pi r cubic, but the only thing is that we need to replace the r with the a value. That's why we need this relation. How we find this relation? Okay, although it's a given in the, let's say, in the formula, but we have learned before how we derive this relation between radius and a, that is the lattice parameter or lattice constant or the unit cell each length. Okay, then I think we can do it. Okay, okay, so for, let's say, for body center cubic, again we know that the number of atoms is 2. I hope that everybody agree. And then for our 3 pi r cubic, but this time the r is different between the simple cubic or from the face center cubic. We have shown before the r is related to a square root of 3 over 4. Okay, we just substitute it here. Okay, and then we know that the volume of unit cell is always a cubic. Okay, because we deal with this cubic system. Okay, the volume. Okay, and then we just substitute it, and we got this one, volume 0.68. Okay, for simple cubic just now we find 0.52. For a body center cubic we have 0.68. So the larger the value of the PF is more, that it become more dense. The density is higher. Why we need, let's say, the dense sample? Let's say for us to fabricate the engineering component, we need the most dense structure. Okay, let's say, but sometimes due to the nature of the crystal structure, we cannot manipulate this, but we can add something, because there is always room or vacancy here. Later on you will find it, in the chapter, I think, diffusion, you will find it, there is a beneficial of having this open or gap. So that's some impurity. Sometimes impurity is also good to strengthen our material. So for the APF for the body center cubic is 0.68. Okay, and then we move on to the phase centicubic. Again, I will show you this one, but later on you need to do the exercise. As I mentioned, all the example will be uploaded. Okay, okay, and then this one, okay, again, we define APM is number of atoms per unit cell for phase centicubic. Okay, for phase centicubic, we have four. I think we have proved this before. Okay, okay, how we got four. And then again the volume of atoms in the unit cell, this is the formula, except that we need to replace the R for the phase centicubic with the A value of each system. So this time is this value, okay, and then okay, and then divide by A cubic. Okay, I think this is still the same. Yeah? Okay, and then we got the 0.74. Okay, that's why the phase centicubic is larger compared to body centicubic and simple cubic. Okay, this is how we calculate. Or let's say if I ask you uh, how to differentiate. Sometimes I'm not asking you the straightforward, but it's meaning the same one. Let's say, uh, let's say for the phase centicubic, example of the phase centicubic. Let's say we have aluminium system, aluminium exhibit phase centicubic. Uh, why it's have the more dense, more APF, more dense structure, means that the atomic packing factor is larger compared to simple cubic. This is how you show it. Okay, and then I think I move on. Okay, I think before we break, I think I can have you another, I think 5 minutes. Okay, for the density composition. Okay, for the density composition, I think we use the formula just now. As again, the formula is given. Okay, what is density? Density actually is mass over volume, but for this one, we define as a mass of atoms in the unit cell. Okay, over the total volume of the unit cells. Okay, and then N is a number of atoms per unit cell, and A is the atomic weight. Okay, again, don't worry, all this formula is given. And what is C? C is the volume of unit cells, and Na times by Na is the Avogadro number. I think the Avogadro number is, I think, is a constant number. It is given by 6.002 times 10 23. No need to memorize it. I think you can refer to the book, and also during the exam online also you can refer all the formula. Okay, should be no problem even for this. So basically what we define as density. Okay, for density, this one we know that we have learned from our Archimedes principle. Density is just mass over volume. Okay, but in terms of the crystal structure, mass of atom in the unit cell, how we calculate the mass of atom in unit cell. First we have to know the number of atom in unit cells, whether it's a body centicubic, phase centicubic, or simple cubic. Simple cubic we got 1, phase centicubic the number of atoms is 4, body centicubic the number of atoms is 2. Okay, times by A, atomic weight. Atomic weight you can get it from your periodic table, or always given sometimes in the problem or in the question that we always mention to you the number of atomic weight. And then divide by VC. VC is just volume of unit cell. A is times A for the cubic, and Na is the Avogadro number. Okay, I think we move to this example before we have break. Okay, okay, chromium has atomic radius of 0.125 nanometer and is a body center cubic crystal structure. When we know that this is a body center cubic, definitely we know the N value is 2. Okay, because it mentioned here. Okay, chromium have the BCC crystal structure, body center cubic. Density is given by N, number of atoms in the unit cell, times by atomic weight. over the VC, the volume of the unit cells times the NA. NA is the Avogadro number, and they always also given us the atomic weight. So I hope that we go through it, but I want one of you to please to check the answer. Okay, sometimes I always make wrong. Okay, so yeah, for the BCC, we know that the given just now. We know that the radius given 0.125, the A is given 52 gram per mole, the N is not given, but we know that although it's not given, we know that the body centimeter cubic should have 2 atoms per unit cell. Okay, and then we know this relation. Okay, how we know this relation? I think it's the formula, and then also we have derived this for the body centimeter cubic. This is the relation between R and A for the body centimeter cubic. Okay, and then I think this is sometimes you need to draw or not to draw, because this one is easy for me because this is PowerPoint. Okay, I have ample time, so I can draw this one. Even not draw, I just cut and paste. Okay, but not from your side. And then from this density is given by this one, and A is then over BC over NA. So we just need to plug in. Okay, we need to plug in into our formula 2. Okay, and then A is 52. Okay, A cubic. Okay, this is where A cubic come in later on. Okay, we need to change this because they only give us the R value. Okay, but we know that the A value have this sort of mathematical relation with R. Okay, so we use this, and it's different for phase centimeter cubic. This one is for body centimeter cubic. Okay, and then we need to change this A cubic to R cubic to R. Why? Because they give us the R value in the question. They didn't give us the A value. So that's why, but this is quite straightforward. You need to replace the A value by the R value. Okay, the R value is given, but we should know the relation between R and A in this body centimeter cubic system. Okay. And then this is my style. Don't worry, I think I need some of you during the break to double check this this value. Okay, and then we just substitute. We know that 0.125. Okay, 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 and then why I got in the centimeter cubic, and sometimes because this is consistent, because sometimes they give you the value in the gram centimeter cubic or gram per meter cubic, but this time I just want to compare to the system centimeter cubic. That's why I changed from meter cubic to centimeter cubic. Let's say if I'm wrong, just let me know. Okay, so we know that the A value is this value, so just substitute, and then we got this theoretical value, and then we just plug in. Sometimes this is the theoretical value, 7.18 gram, 7.1 gram. So I hope that, let's say if you are asking for phase centimeter cubic, you need to find, the only difference is that you need to consider the number of atoms, the N value. Atomic weight of course is different from every element or metals, but the most important thing is that you need to find the A relation with the R. Let's say for phase centimeter cubic, there is another relation we have seen before, and let's say for simple cubic also we have another relation. So two major important points that you need to consider is that the number of atoms and the A value, because A is related to the R and R is different for each system. Okay, then I think just to sum up, for this session before we have breaks. We have described the atomic arrangement for crystalline and non-crystalline. Okay, just to recap, crystalline can be divided into polycrystalline and single crystalline, and then we have learned how to draw it. And then we also have the non-crystalline. We call this as amorphous. This is amorphous. Okay, and then we also have learned we learn how to draw the phase center cubic. Okay, it's a simple one. If you draw like this, I think it's acceptable. No worries. And we also have the body center cubic, and we need not to worry about this HCP. Okay, we have managed to draw it, but later on during the exercise, I hope that everybody can draw it. Okay, and don't worry. Let's say if you have a problem, just let me know. And then okay, to derive the relation between unit cell H length and atomic radius for a free centicubic and body centicubic crystal structure. Okay, we have covered this. Another important thing is just the simple cubic. Okay, and I think lastly is just the density punya equation. Okay, we have learned about free centicubic and body centicubic. Let's say if I ask you the simple cubic also, I think the same method apply. Don't worry, I think the most important thing is that, as I stressed before, you should know the number of atoms for each cell of each system of each crystal structure, and the A relation between R that is different from each crystal structure. And then draw a cubic. Okay, later on I think don't worry, I think basic height level since it's a cubic. Okay, sorry. Okay, so sorry. Oh, I didn't see the chat box because me, sorry. Okay, okay, what is the A? Is the height? A is the image length. Good. Then has answered for me. Thank you, Yan. Okay, is the height length since it's a cubic. Great. Okay, sorry, Salina. I didn't realize in the chat box because when I present, I cannot see this. Okay, class, can we have break for let's say 5 to 10 minutes before we start? Is it okay? So I confuse you. Okay, I think this is start up from email. Okay, thank you, email. Okay, can we have breaks here? And then we start to do this exercise together. Okay, sure. Okay, thank you. Thank you, guys. Okay. So, so the class, shall we start again? Is it okay?
Yeah, doctor. Yeah, it's fine.
Okay, thank you, yeah. Okay, sorry for this time, yeah. Okay, so, okay, okay, that's great, okay. Okay, this one, I will not ask you to this one. Okay, we just do it together. Okay, but later on, maybe, before, let's say, the exam online, we will have, a revision class. Okay, let's say this one, draw a cubic, straightforward. And then if I ask you to draw a cubic, and then how many edges are there in the cube, how many corners are there in the cube, I think it's just, this one is, so what this is just uh, for your understanding. Okay, you will not see this type of question. Okay, so draw a cubic, you just draw like this. Okay, and then how many edges are there in the cube? I think everybody know 12, yeah. 1, 2, 3, 4, 8, and then another 4 here. So there is 12 edges. I think we just, I think it's just simple maths. How many corners? Should be 8, and how many faces? Should be 6, yeah. Then we go to, let's say they ask us draw example of a face diagonal. I always mention to you, this is face diagonal. Okay, face diagonal. And then draw a example of body diagonal. Don't worry, I will show you what is meant. I think this is repeated and if the each length is A, okay, all this A length is A because it's a cubic, should be same. And what is the cubic volume? I think we have done this. This is just exercise. Okay, what is the length of a face diagonal? I think we use the simple theorem there. And then what's the length of the body diagonal? So this is the draw a face diagonal. Okay, this is face diagonal class. Okay, I will enlarge it. Just to, although I think quite repeat. Okay, this is face diagonal. Face diagonal is very important, as I mentioned before, in measuring the relation between A and R for the face center cubic. For the body diagonal, this is body diagonal. Okay, why it's important? Because I mentioned that for the body center cubic, we need to measure this length because this is only where all the atoms are touching each other for the body center cubic. Okay, and then okay, if the length is A, I think it's simple mathematics. Okay, and then what is the cubic volume? Again, this is just repeating. Uh, okay, and then the volume is A times A cubic. Okay, and then what is the length of the face diagonal? You just A squared plus A squared means that the FD, the face diagonal, uh, is square root of 2A. Yeah? And then for the body diagonal, okay, you find this body diagonal is just the this one FD squared face diagonal, okay, plus face diagonal is this one plus this one D squared. Okay, I think quite straightforward. It's just this one, and the body diagonal is okay. I think it's I hope that it should be no problem for all of you. I hope that okay. And then okay, I think it's a good one. Okay, draw this one. I will skip. I think you have done this, but definitely this is how we draw it. Okay, I hope that I will go through it later on. Okay, don't worry, I think this is too easy for you. Okay, like Yan said, it's a white peanut. Okay, for everybody. And then how we all of the, let's say, whatever exercise assignment are in the lecture notes or in the books. Yeah, okay, this is just example. I hope that you can I will go firstly this one. Yeah, I think if later on, let's say we will have a revision on it. I think it's quite straightforward. This is sort of the assessment. I think I've covered this in the lecture. I hope that you don't mind. I go fast. We have calculated all these. Actually, whatever I have taught you, actually is good for your assignment and quiz as well. Okay. Okay. Is it okay, class? I go like this. Is it okay? Because we have covered that, and then maybe later on we have a revision before our exam online. Is it okay? I just keep that because that thing, all these are covered in the lecture. Is it okay?
Yes, it's okay, Doctor. Also, Doctor, can you add the student Hasman Akit to the MS Teams? He registered already, but he's still not in the Microsoft Teams for some reason.
Okay. Can you send me his email? Is it okay?
Okay, his email. Hasman, drop your email in the chat box.
Okay, in the chat box. Later on.
Yep.
Okay.
Sir,
Sorry. Yeah.
Sir, I have not also been added to Microsoft Teams.
Okay. Kindly please give me your email. Is it okay?
Yes, sir. It is. Okay.
Yeah, I can see your email here. Okay, but later on I will this one. Is it okay?
Yes.
Just email. Yeah. Is it okay?
Sir, I have a couple of questions. Can I ask?
Yeah. Sure. Before this is okay. Then I think I'll just stick to the simple diagram.
Okay.
So
sir,
what is it? Yep.
Yes, sir, and on the study materials, I understand most of it. I don't have any problem so far. But sir, I have some questions like, sir, how do we proceed about the attendance, sir? Because I have been registered late, so I missed the first class.
Oh, don't worry. The first class is just introduction, but you can ask me to repeat it personally. Don't worry. Okay, or you can, let's say there is a video on it because we recording. But let's say if you have any problem, definitely I will explain to you. Is it okay?
Yes, sir, it is okay. And sir, for attendance, do I need to register on Power app? Or
there is one option, but don't worry. In every lecture, I will download your attendance for everybody. Is it okay?
Thank you so much, sir.
Okay, great. Okay, this to be added to MS Team. Good. Yeah, this always good. Okay, can we proceed? Is it okay? I will do it later. Is it okay? Yeah. This Muhammad punya ni case. Yep. Is it okay? Yeah.
Yes.
Okay, great. Okay, don't worry about this. We will rectify it. Okay. Alright, and then we move on. Okay, yeah. So this the another important thing that we shall cover today is the direction and plane. Okay. So what I think is also quite straightforward. No worries. Okay. There is also they will ask you, let's say sketch or draw, let's say the plane or the direction. Okay, don't worry. Okay, then move on. Okay, this is energy packing. It's about the random packing for the dance. For the dance, they have the order packing. Okay, then this is the typical energy and the R punya relation. Okay, and then we move on to we know that unit cells. Okay, ABC are the lattice constant, but as I mentioned, in our system we are using cubic system, means that A is equal to B and also equal to C, because we are dealing with the cubic system. Okay, whatever in this course we are only dealing with the cubic system. Okay, what we are going to learn today? We are going to learn the direction. Okay, the arrow. Okay, you can see this. Let's say later on, when you let's say work, sometimes if you are dealing with the quality control punya department, okay, or you are assigned, okay, sometimes you have to do the XRD, X-ray diffraction. So this term they always mention. This is the square bracket, and this plane. Okay, later on I will mention what is the difference between square bracket and bracket. Okay, so we move on. Okay, I think this direction you are for most important thing before we start or whatsoever. So first of all, we call this axis x. Okay, this is our origin. Okay, you can define. There are many type of books. Yeah, you can define. But our this one, I hope that you will stick for this definition. But I'm not going to say that you are wrong. Let's say you put this as x or this is y. But for this, I think you should state it. Okay, for this one is x-axis. Okay, this is our origin. Move forward, we call it a plus x, and move backward is a minus x. Okay, this one is just coordinate. This is just to describe point, not yet touch the direction and planes yet. This is just direction. Okay, for this one, if we move this one, I think it's quite clearer. The coordinate for this one is 100, and for this one is minus 100. Similarly for y-axis, this one is 010. Okay, means that we are moving into this direction. Okay, the right hand side 1 and the left hand side is a minus 1. Okay, and then what else? Yeah, for z direction as well. Okay, for z direction, 001 for the going up is 1, going down is minus 1. Okay, I hope that everybody is clear. It's just a coordinate for this system. This is our origin, 000, 000. Okay, we move on. Okay, let's say at this point. Okay, how we define this point? Okay, we move here, we move here, we move here. That is our coordinate. No worries. Let me show you example. No worries. Okay. Okay, let's say this one. The point coordinates of this one is A, is 111, because okay, we in order for us to this one, we have to move here. Let's say 1 in x direction, y positive y 1, and then we have to move up 1. That's why the point coordinates of this one is 111. Okay, then we move on. Okay, similarly for the okay, this is just the one that I explained earlier. Okay, so for the point A, I think it's for point A, quite, let's say it's point A, it's quite straightforward. We only move in the Z direction. This is 1 unit. So we call it as a 001. Okay. Okay, we call it as a 001. Okay. D is similar for this one, and also B, and also for C. Okay, so for C we have to move 1 here and half of x direction, and no 0 direction or 0 value for the Z direction. Okay, this is for the direction. Okay, okay, this is direction. Okay, there is a way how to calculate this one. Either way, I think is acceptable. Okay, for this one direction, I think the direction is quite important. Okay, and definitely I will ask during the, let's say, quiz assignment, and let's say for the assignment as well. But don't worry, it's quite straightforward. Just let me know. Okay, so I think I will this one. The most important thing is that, you know, this is my style. Whatever is, I don't force you to follow this, but this is the step that you need to do. Okay, there is many ways. Okay, definitely many ways, but this is one of the ways. Okay, x-axis, as I mentioned, this one is x, then this is y, and this is z. Okay, for the head, let's say this is for the head. It's just, let's say, the head is the one with the arrow. Okay, we find it as the x2, y2, z2. Okay, this is the coordinate of the of the head. Yeah, so we call this head, and this is we call as a tail. Tail we call it S1, Y1, and Z1. Okay, because it's start from origin is 000. It's no problem. So then, in order for us to find the direction, okay, crystal direction, we have to have head minus tail. Okay, head minus tail is like just head minus tail. Whatever value you just minus it, and then reduction means that we don't want any fraction. Okay, later on I will show you the example. No worries. And then this is the final answer. And for the direction, it should be square bracket. Okay, square bracket. Okay, this is square bracket. Don't worry, later on I will show you many example. Okay, means that there is no reciprocal involved. Okay, we don't want our final answer to be have the fraction value. Okay, again like this one. Okay, again I will show you. This one we have the coordinate. Okay, let's say this one is a half. Okay, half. The distance is half of the this one is half. Okay, for let's say head. Okay, the head. So the head is the coordinate is 1 in the extension, because we have to move to the front. Okay, and then we need not to move in the y direction, or the coordinates doesn't involve any y direction. Okay, I hope that is not from okay, and then we have z direction is half. Okay, the coordinate of z, so you put it 1 0 half. The tail is here is our point of coordinate, the origin, as I mentioned, 0 0. So what you need to do later on, head minus tail. 1 minus O is 1, 0 minus 0 is 0, half minus 0 is half. So then, as I mentioned, we have to clear the fraction or reduce the lowest integrals. That's why we times by 2. Are you agree? Yeah, I hope that you agree. In order for us to eliminate this fraction, so once you times by 2, 1 times 2 is 2, 0 times 2 is 0, half times 2 is 1. So our final answer, the direction should be, I always mention, should be in the form of square bracket. This is your word example. This is just your step. This is your direction. So your direction for this one is 201 in the square bracket. Okay, I repeat again. So first you need to do, okay, let's say you know this is half of z punya length. They should indicate, this is half or 3/4, but this case is half. Okay, this is stated, no worries. Okay, so the head coordinate of the head is, this in y is 0, not to the coordinate is 0. For x is 1, because we have to move here, and then the z is half. The tail is 0 0 0. Later on I will show you. Always put your tail as 0 0 0. Quite easy. Okay, and then what you need to do is head minus tail. 1 minus O is 1, 0 minus 0 is 0, half minus 0 is half. So then, because there is half here, you need times by 2 in order for us to eliminate this half. Okay, that's why 1 times 2 is 2, 0 times 2 is 0, half minus half times 2 is 1. So then your final answer is 201, should be in the square bracket. Okay, then Okay, all of you, please do not leave this lecture because I haven't downloaded your attendance. Yeah? If you leave, then I'm afraid that I cannot capture. Yeah? Okay, let's say the similar from this one. Okay, point tail 1 to point head 2. As I mentioned, you can do this as your punya point of origin, means that your tail is always 0 0, or you can use this as point of 0 0. Either way, it will give you the same answer, but for, let's say, for easiness or for quick one, we should put it is as the 0 0 0. Really, I will show you. Okay, there is two answer. Yeah? Okay, this one I put the tail as the 0 0 0. I think this is most convenient way. Okay, but let's say if you want to put this as a 0 0, your point of origin, it doesn't matter. It will definitely give you the same answer. This one I refer this one as the point of origin. So means that your tail also has to follow this point of origin. This one, your point of origin is always your tail. Okay, we concentrate on this one first. Okay, for this one, what is x point of coordinate? Okay, your head is one. Okay, you have to move this half. Okay, this half is a positive direction because we move into the right one, the right direction. And then what is the value of x? Because this is 2 cubic, means that we have to move one here and one here. So they become the minus 2. Yeah, -2. And then another important I will stress later on. Okay, just please stay with me. Don't worry, there are many exercises for it. Don't worry. Later on, one we has covered all this before your, let's say, quiz or exam online. Definitely we have the revision. Okay, and then what is your z value? The z value is just 1. Agree? We just move up in the up position. That's why it's positive 1. Okay, I hope that everybody agree. But this time, please, if you, because I can see the chat box, just interrupt me at any time. Yeah? Okay, and then your tail become your point of origin, 0 0 0. Your tail become point of origin. So and then, as I mentioned earlier, we have to hit minus tail. Okay, minus 2 minus 0 is minus 2. Half minus 0 is half. 1 minus minus 0 is 1. But there is always fraction here, right? So we want to eliminate this, then we multiply by 2. So minus 2 times 2 is minus 4. Half times 2 is 1. And then 1 times 2 is 2. So as I mentioned, your final answer should be in the bracket. That is minus 4, 1, and 2. But one another important thing is that for the direction, okay, you have to, the overbar means negative index. Your final answer should be like this. This is just your work example. Your final answer, your minus should be up here. Okay, please remember that. Okay, and should be in the square bracket. The square bracket will differentiate between, later on you will learn about plane. This is the direction punya square bracket is for direction, plane is a bracket. Okay, and another thing is that you can also appoint this one as a point of origin. Okay, but it takes times, but it doesn't matter. Either you want to choose this way or this way, it doesn't, it still give you the same answer, except that this one is straightforward. Okay, this one you have, let's say head. Head is from here, let's say your head is here, you have to move here in the -1. Agree, you have to move here, okay, in this -1 backward. And your y, because you have to move in your right hand side, +1, and then you have to move up is 1, so you have to move here, here, and here. So -1, 1, 1. And for your tail, you have to move here, +1, and then is half. So this one is half, yeah, half is positive half, and there is 0. This is your tail coordinate. And again, head minus tail is like this. -1 minus 1 is -2. 1 minus half is half. 1 minus 0 is 1. So as again, we don't want any fraction. We need to times by 2. It's become -4, 1, and 2. It gives you the same answer. But your final answer should be like this. Okay, this is only in your what we call it, in your step. Okay, and your final answer should be like this. Okay, and you should be square bracket. And some I have encountered from my previous experience, the student lose mark because they didn't put this one. But please put this one, and then the square bracket also. Sometimes they confuse the square bracket and the planes. But later on, when we learn planes are in the in the bracket. But for the planes, bear in mind it should be square bracket. Okay. And then, okay. This one means that okay, because we know that vectors direction. If let's say if we have a square bracket of 101, this is direction, and -101 is not identical. But this one, 100 and 20 are identical because they are in the same direction. Okay. Okay, direction is multiply identical. Okay. This one is not identical. Okay. Okay. I think 10 more minutes. Okay, let's say we do, let's say one example or two. Okay, or I skip this one. I'll show you this one. I think we'll skip this one first. Okay, let me do this one. It's not nice. Okay, let's say we do the A. Okay, this is A. Okay, this one we do together, yeah. Later on when we have land, we will definitely should practice. We will practice also together, and then I will check it. I will random it, call you. I hope that, and then you just snap your let's say picture and then post in the WhatsApp group or in the MS Teams. It doesn't matter. Okay, let's say, but this one I do it together. Okay, let's say I think I will do it 1 and B for you. Okay, then we reserve it, I think, and then we want to tidy up because next week is West Day. I want to have a consensus whether we should continue our lecture because I have to respect. So let's say if you don't want, because that one is holiday, but then we have to decide when is the availability time. Okay, we have to, and then I depend on solely on Yan to gather all the information from you guys. Okay, so then we try A. Yeah? Okay, we try A first. Okay, let's say for A. Let's say for this A. Okay, later on I will this one. Let's say for A. Let's say for A. I always mention to you that this one will be your point of origin. That is 0, 0, 0. Okay, means that in order for you to here, you have to move down in the y direction, that is in the z direction. Sorry about that. Yeah. So this one you should label, this is for x. Okay, I will write for you. Sorry for this one. Okay, sorry, this is x, this is y, this is z. So in order for you, you should use head, axis X, Y, Z, and then head, and then tail, head minus tail, and then you do your, let's say, reduction, means that we don't want any fraction that we call as enclosed, and then your final answer. So in order for you to move to here, uh, you have to move down. That is means our Z is -1. Okay, and then you have to move forward for acceleration, means that our X is +1, and also our Y is +1. Okay, and then you just minus that, and you will got this answer. Okay, so this card. Okay, I hope that you can see this. Okay, so our this one is quite straight, this, but I hope that you will follow this, uh, this table, 8 minus tail, this one just for a quick one. Okay, means that our X is 1, and our head of X is 1, Y is 1, and Z is -1. So just our tail is 0, 0, 0. That's why our final answer is this one. Okay, for B, I think is in order for us to move to here, we have to move in up front with the X direction is half of X, that is half positive direction, and then -1 because we have to move in the left hand side for Y, -1, and then for Z is 0. Okay, okay, and then because there is a fraction here, we need to times by 2. Okay, and then this is our answer. Okay, the 0 is I mean the minus should be in upper, our head, but no need to follow like this. But let's say if you follow like this, is okay, but I hope that when I ask you, I hope that you will draw nicely like this. Okay, I think I'll stop here because next I think we will touch on plane. Okay, so I think I open this for discussion. First I have to download your opinion. Download attendance, otherwise we are in trouble. We are in trouble. Attendance. Okay. Guys, any question, guys, for this matter on how to pass, or let's say don't worry, later on I will still give you more example, and whatever solution that we have gone through together I will upload. So any question, guys? Hello?
No question.
Okay,
So far,
so
so good.
okay, thank you. So for the next week, it's holiday for Wesak Day. So can one of I want a consensus whether we should proceed on that day. So because if we proceed on the day, it's not fair to our colleague who who celebrating this Wesak Day. So any suggestion, class?
When would be the available time for doctor?
Okay, for me, okay, I have class on, let's say, Monday and Tuesday. Thursday should be fine for me. Or let's say for the Tuesday also is can, but can we do it, let's say from 2 to 4?
Tuesday 2 to 4. Yeah, that can be done.
Yeah, okay, that's great. So means that for next week punya lecture, I will invite you through MS Team from 2 to 4, 2 to 4, yeah, on
Tuesday.
Tuesday.
Got
Yep.
it, sir.
Okay, great. So I hope that I'm not going too fast. I hope that everybody understand. But let's say if you have any problem, just just inform me. Yeah, I will do. Let's say, let's say whatever revision or whatsoever class, extra class, no problem for me. Okay, and then you can always, personally WhatsApp me or in the WhatsApp group. Let's say if you have any problem. Is it okay, class?
Yep, it's all right.
Okay, so thanks, class. And then I shall add this Muhammad and Hussein. Can you share me? Okay, hang on, hang on. I will do it now. I always forget. Sorry about this. Yeah, hello. I will add this one. Manage tip. Add member. Okay, please. Muhammad Al-Fikri. Okay, add. Okay, Muhammad Azman Akid Fikri I have add. So how about what is it? This guy, Iftikar.
Yes,
Iftikar.
sir. Yes,
Can
sir.
I have your? Can you just? Okay, I think I can. Your punya ni. Okay, I can. This one. Okay, sorry. I think I can get your copy your, let's say, contact number. Don't worry. Okay, I go back and then manage tip add member. Okay. Okay, I have also added you as well. Okay, guys, great. And one more thing, if I hope that you can do the feedback every time. I'm sorry about that, and I think I have to end of this meeting so that we can have a proper recording. So let's say if you have any problem, I also thank you to all of you with me. Okay, for this nearly 2 hours. Thank you very much for your time. Although it's bored, I hope that you gain something from it. Okay, hopefully, inshallah. And then I hope that you will do your, let's say, feedback. Yeah. Okay, I hope that. And I think I will invite you to MS Team, and I also will download the recorded version, or you can also in the ULearn, and also in our MS Team is automatically downloaded. And definitely later on I will upload all the uh, example that we have that we have done together. Okay, thank you guys. I hope that you have also have a great day. Thank you to everybody. So I have no chance to meet you face to face. Maybe later on after the COVID MCO, hopefully we can meet, yeah, face to face. Okay, I think it's a great class. Okay, thank you very much. Okay, see you. Okay, see you soon. Okay, thanks.
Thank you, sir.
Okay,
Thank you, sir.
thank you. Thank you, Nazrin. So I'm sorry, I can't remember all of you, but like Niza, Salina, I remember Yan, Nazrin. Don't worry, yeah, I will try to my best, to know each of you. Okay, thank you very much for your time.
Thank you very much, sir.
Okay, thank you. Yeah. Okay, bye.